Hi, my name is Leandro Lanzieri.
And I'm Kietzmann. Today we are presenting our paper Secure and Authorized Client-to-Client Communication for Lightweight Machine-to-Machine. This is joint work with Thomas and Matthias.
The success of the growing Internet of Things brought up many heterogeneous embedded devices being interconnected through the global Internet. An ever-increasing number of vendors deploy their own proprietary ecosystems and contribute to the building of incompatibility silos as devices cannot communicate with one another. As usual, Internet-exposed devices make a desirable target for attackers. Therefore, the usage of modern but lightweight security mechanisms is mandatory. Common Internet of Things devices have limited resources. They consist of low-power microcontrollers with constrained processing capabilities and memory. These devices often have a tight energy budget and communicate via lossy wireless links with small packet sizes. The IoT serves as a variety of use cases, including distributed applications with edge collaboration, ranging from industrial control systems with low latency requirements to residential deployments where privacy is paramount. This also includes remote and mobile scenarios with expensive or intermittent uplink connectivity. Lightweight machine-to-machine, or LwM2M, is a widely deployed IoT management protocol that helps tackling many of these challenges. Unfortunately, it lacks functionalities to enable IoT applications being distributed on the edge. This is the starting point for our work. We provide extensions that enable distributed LwM2M applications where a server-centric communication architecture is not the best fit. Thereby, we still leverage existing features of the standard protocol.
The LwM2M protocol provides IoT device integration on the higher layer of the network stack. It is defined over multiple transport bindings and allows different security options. In this work, we focus on DTLS, which is session-based, and OSCORE, which is object-based security. LwM2M provides semantic interoperability across vendors by defining a resource and interaction model. It further enables features like resource access control, device bootstrapping, or software updates. The specification defines two entity types, LwM2M clients and servers. In the standard deployment, operations on clients are only performed by servers using secure communication channels. This requires credentials and access rights. Cloud-based IoT applications interact with clients only through these servers. The imposed server-centric communication in LwM2M prevents edge collaboration, one of the prevalent scenarios of machine-type communication. LwM2M clients expose their operating information as resources which are grouped into predefined objects. These objects accept multiple operations such as read, write, or execute. To control which operation a server can perform, access control policies are in place and manage permissions.
Our extensions enable client-to-client communication in LwM2M deployments. Here we present an illustration. By allowing clients to perform operations on other client resources, application logic can be moved and distributed to the edge. This keeps a big part of the communication locally, reducing latency and increasing bandwidth. On this setup, servers remain as client monitors. To achieve a client-to-client communication, clients require credentials and access rights. This information is contained in new LwM2M objects. Together with the extension of existing interfaces, which allow client operations and handle client access rights, this conforms our first core contribution. To achieve more flexibility in LwM2M deployments, we additionally developed a third-party authorization mechanism. It enables clients, upon need, to dynamically request credentials and access rights to servers. This conforms our second main contribution. Let's see a sequence example of the mechanism. Client 1 intends to communicate with Client 2. First, Client 1 needs to discover which server can provide credentials. To this end, an optional initial unauthorized request on Client 2 triggers a response with owner server hints containing information about the server. Then Client 1 can request the necessary credentials and access rights for Client 2. If the request is accepted, the server proceeds to install them on both clients. With the credentials distributed, the clients can establish a secure connection. In the case of DTLS, a handshake occurs at this point. Over the secure channel, Client 1 can now perform the necessary operations on the resources of Client 2.
Now let's move on to the experimental evaluation of our extensions. We deployed two LwM2M clients which reflect a sensor actuator use case. They form a multi-op topology with varying distances to a gateway, and the LwM2M server on the cloud manages our clients. IoT nodes are operated with the IoT OS Riot and the Vakama LwM2M implementation. The server uses a modified version of LashArm. We conduct the experiments in the fit ITLab testbed. The M3 nodes in the testbed provide an ARM Cortex-M3 microcontroller which runs at 72 MHz and provides 64 KB of RAM and 512 KB of ROM. M3 nodes further include an 802.15.4 wireless transceiver.
We first take a look at the memory footprint. As a baseline, we consider the requirements of a basic client implementation. The figure also shows a share of the relevant modules on the complete firmware image. When we add the client-to-client functionalities, we see a slight increment in both RAM and ROM. This is attributed mainly to extra client handling code. In turn, when we compile in the third-party authorization feature, we observe no extra RAM usage. The client-to-client feature requires only an additional 3% of ROM and 1% of RAM, while the authorization uses an extra 5% of ROM. Using the previously introduced setup, we measure how long it takes for a notification from client 1 to reach client 2. Between clients, we used first DTLS and then OSCOR security. To filter the variable internet delay, we offset the server-centric measurements by the median delay. This establishes a base of around 80 milliseconds. We can observe a systematic increase in the delay with the number of intermediate hops. In turn, when the client-to-client communication is used, notifications arrive in the order of 10 milliseconds. Zooming in, we observe that OSCOR is faster than DTLS. This shows that client-to-client communication reduces the notification arrival times by roughly 90%. We then run the same experiment on randomized topologies, which yielded the same results. Now we consider a scenario where a client requests credentials and the server installs them. We see that 50% of the times the entire process finishes in under 1 second for DTLS. The observed staircase pattern corresponds to the co-op retransmissions. We conclude that the distribution of OSCOR credentials slightly increases time and retransmissions due to an additional object being distributed. Then we trigger an initial client-to-client operation. We observe that for OSCOR, the times are in line with their previous measurements, while for DTLS they increase up to 160 milliseconds. The time of the initial client-to-client operation for DTLS is slower due to the required handshake. Next, we look at the effective Goodput achieved by each setup. We send fixed size notifications at different intervals. For the client-to-client communication, we observe an almost optimal behavior with a steady delivery rate close to 100%, which only starts degrading as approaching 10 milliseconds. On the other hand, the server-centric setup reveals a maximum Goodput of around 50 bytes per second and a degradation of delivery rate for intervals below 100 milliseconds. We conclude that the Goodput on client-to-client scenarios is 8 times higher than in server-centric ones. During the experiments, we register the total energy consumption of the nodes, which is mainly impacted by the amount of intervening devices. When compared to the single-hop server-centric scenario, the client-to-client deployments show no energy impact. We can conclude that client-to-client feature comes at no energy overhead for individual nodes, while the usage of less intermediate hops reduces the overall energy requirements.
In this work, we have contributed a third-party authorization mechanism for LwM2M clients. New objects and extended interfaces enable client-to-client communication. We have performed experimental analysis on off-the-shelf IoT hardware. Our implementations are publicly available. Our results show that client-to-client communication reduces data arrival times by up to 90% and yields a more reliable and 8 times higher Goodput at moderate memory footprint. In future work, we will analyze the applicability of the ACE-OAuth framework to LwM2M and explore the integration of group OSCOR to improve multi-client observations. Thank you for the attention.
We support reproducible research. You can find our code available on GitHub.